Good afternoon, class. In today's video, what I'd like to do is to continue my series on collisions, and this time we're going to do inelastic collisions, whereas in the last part we did elastic collisions. So basically what I tried to do is keep all of the diagrams the same. It's still car A and car B. One of them, car A is traveling with a forward momentum, P1. Car B in the first part is going backwards, going towards car A in a head-on collision. And the second one is going to be car B is going to be moving in the same direction as car A. So in both cases, we're going to assume that this direction is positive and this direction is negative, just again to keep our norms consistent. So in this case, I made some assumptions, again, separated out by my red line, that we're going to assume in this case that M1, the mass of both cars, car A and car B, are the same. We're going to assume, again, this way is positive. We're going to assume that the initial velocity is 10 meters per second. And we're going to assume that in this first one, when car B is traveling towards car A, it'll be traveling at -5 meters per second. Of course, again, to point out, why is it negative? The reason why is because car B is traveling in the negative direction. And that's the case. That's the reason for it. In the second part of this, we're going to let the initial velocity of car B going in this direction be +5 meters per second. So basically car A is going to rear end car B, whereas in the other one, car B and car A are going to have a head-on collision. So that's the setup for this problem. So what I do now is I pull together all of my inelastic collisions and see what happens. So I've got M1 V1 initial plus M2 V2 initial equals, in parentheses, M1 plus M2 times the new final velocity V final. So in this case, it's a little bit easier. I don't have as many assumptions because I don't have a little less moving parts. And we'll get to see and compare, because basically I'm doing the exact same thing between these two sets of videos. Which one will be a little bit more on the realistic side? So we'll see. Stick to the end. We'll see how that goes. So what I do now is I'm plugging in all of my assumptions here, and I'm going to plug them into this equation like so. So I make both of the masses M1, and you'll see why I do that in a little bit. So then I plug in V1 initial 10, V2 initial -5. Again, instead of M2, I'm going to put M1. And again, could I put M2 for both of them? I could. As long as they're the same, then it's fine. So you'll see why I did this in a second. So 10 plus -5 is going to be +5. That's times M1. That's what I get here. M1 plus M1 is 2M1. So I've got 5M1 equals 2M1 V final. Now what do I do with that? Because I've got that mass that I still don't know what to do with. However, I do have a solution for that, and that is to divide both sides of the equation by M1. Now, the only reason that this doesn't work is if M1 is 0, because then we're dividing by 0, and that's not allowed by math. So as long as the M1 has any mass at all, this assumption this tool that I did by dividing both sides of the equation by M1, it works. So keep that in mind. So we'll be working on that we'll be going through with that assumption, assuming that there is mass for both of these cars. So your final velocity will be 5 divided by 2, or 5/2 meters per second. What that basically means, if you're to look now at the change in momentum for both of these cars, like if you were looking at each individual car, that would say that car A smashed into car B and continued to go forward, albeit at a much reduced rate. It's going forward a lot slower than it was. Car B, on the other hand, not only smashed into car A, but changed its direction and went out, at a reduced rate, but still in the complete opposite direction. So the change in momentum, if you were in car B, would be so much greater than it would be in car A. So something to think about, especially if you think about all the scenarios about which car, especially when you look at car crash pictures, one car usually is in a lot more trouble than the other car. One car gets more damage than the other car, and that would be why. And so what it's trying to tell you is that when you see car crashes, they're generally going to be inelastic. They're not going to be elastic because we don't build our cars that way. And that's actually on purpose to make sure that it's more survivable for everyone involved. That's the goal. Okay, so that would be what happens in the first scenario, in the blue scenario. Let's see what happens in the green scenario. So in this case, car B is going in the same direction as car A, but they're now going to smash and they're going to collide and they're going to stick together. So in this case, again, the same thing, same holds. M2 is going to be equal to M1, so that's why I leave it as, I just made them all M1 just to keep consistency between the two examples, and I do that so that you can see what I'm doing and how, and the very small differences that I made, so that the physics comes through a whole lot more. So in this case, car 2 is traveling at 5 meters per second, not negative 5 meters per second. So they're going to, so when they hit, they're going to combine the masses. So in this case, M1 10 plus 5 is 15. So 15 M1 equals 2 M1 V1 V final. And so what we have now is when we divide both sides of the equation by M1, we get 15 divided by 2 is your final velocity, which hopefully does make a little bit of sense, because, you know, if car, in this scenario, if they're moving together, car A hits car B, but because car B is moving in the same direction, car A slows down, but not nearly as much as it would if there was a head-on collision. Car B, on the other hand, speeds up a little bit because it got hit, and so it's going to go forward, or it's going to go forward at a faster speed than it was going at, but not as much as car A, because of this extra mass that is held between the new system of them being stuck together like that. So hopefully what that tells you is that, you know, in the last video I talked about how the assumptions have to be right, and this is very not realistic, but mathematically it works. What that tells you, hopefully what that you start to see from both of these examples, is that most of the collisions in this world, realistically, are inelastic. Most of them. There are very few purely elastic collisions. In fact, there are very few elastic collisions, like, at all. Most of them are some mixture of the two. And there are reasons for that. There's thermodynamic reasons for that, which I can get to in another video. But really, anything that where energy or momentum doesn't completely get transferred from one object to the other, that's generally going to have some measure of an inelastic collision in there. So think about that. Hopefully that kind of, you know, although some of these, I mean, these kind of scenarios are a little bit, they can be a little bit, I mean, they're common enough that you see car crash pictures. So it's something to think about, especially in terms of safety. If you're going to be a safety engineer, you want to design it so that no matter what that velocity is, no matter what the mass of the car is or anything, people inside the car are going to survive. And that's why so sometimes when you see, one thing I do want to point out in terms of safety is one of the reasons why car crashes look so horrific, for lack of a better word, is because what's going on is those cars are getting mangled when in the crash with each other, and the reason they do that is actually by design, because then the energy of the collision is not going through the system. It's going and compressing and crushing and destroying parts of the car, and those parts are basically sacrificed to keep the people inside the car alive, and that would be you and me. So that's something to think about. The whole reason that everything kind of sprays out from the car is to keep the momentum that gets transferred to you, or you and me, minimal. And it's all about survivability. So it's something that I want you to think about in terms of how would you be more safe in when you design certain elements, especially if you're going to design a car or anything really, and safety is a concern. You know, how do you keep things safe? And hopefully this inelastic collision will help you at least conceptually think about how to do that. So that concludes this video on inelastic collisions. Good luck in your studies. May the force be with you.